Hello, welcome back to the playlist of topics on regression models and statistical machine learning. I am Hemukumar Kasala, and as part of this video, we continue our learning on multicollinearity in multiple linear regression models. In the second part of the video on multicollinearity, we learn about the statistic variance inflation factor VIF to measure and quantify multicollinearity. We learn how to derive a general expression to calculate VIF. We learn two commonly known types or causes of multicollinearity, namely data-based multicollinearity and structural multicollinearity. And finally, we learn how to deal with each one of the types of multicollinearity in model building. Let's get into the video. Lecture 14, Multiple Linear Regression Multicollinearity Part 2. We understood the impacts of multicollinearity on the regression models, analysis, and the subsequent conclusions that we draw. How do we measure multicollinearity to say if it exists or not? We learned multicollinearity can be detected by observing the changes in the estimated slope coefficients between the models, variance associated with the estimated slope coefficients, t-statistic and p-values for estimates of the slope coefficients for every predictor variable, and correlation between pairs of predictors. Correlation is not necessarily restricted within pairs of predictors. It can exist between 3 or even more number of predictors. We have not learned how to measure multicollinearity yet in order to decide whether to accept it and allow it in the model or to take actions to minimize or eliminate it. Here it is, variance inflation factor. VIF is the one that analysts often rely on to measure multicollinearity. We encountered VIF figures in the Minitab data outputs that we discussed so far, but we deferred going into the details. Now is the time. As the name suggests, variance inflation factor VIF measures the inflation in the variance, meaning variance associated with the estimated slope coefficients. As can be seen below, which we had earlier discussed as well, the estimated standard deviation, which is the square root of variance of the estimated slope coefficients, are much lower when only one among the two correlated predictors is included in the model, as compared to the model where both predictors are included. We see the variances are inflated when both predictors that are highly correlated are included in the model. In case of weight, the estimated standard deviation, which is the square root of variance, is inflated to 0.193 from 0.0930. And in case of BSA, the estimated standard deviation is inflated to 6.06 from 4.69. Variance inflation factors, VIFs, quantify these inflations. VIF, which equals 1.0 when one of the two predictors is included in the model, inflates to 4.28 when both predictors that are highly correlated are included in the model. Variance inflation factor is calculated for each predictor and the value is given by VIF k equals inflated variance k divided by minimum variance k, where minimum variance k equals variance of the estimated slope coefficient of the kth predictor when it is included alone in the model. Note, variance is minimum when the model does not include other predictors that are correlated to the one included in the model. Inflated variance k equals variance of the estimated slope coefficient of the kth predictor when the model includes all the predictors, including the ones that are correlated. Accordingly, VIF weight equals inflated variance of weight divided by minimum variance of weight, which equals 0.1932 square divided by 0.0932 square, and that equals 4.28. Note, 0.1932 and 0.0932 are the standard deviation values, and since we are taking the ratio of variances, their respective squares are included in the formula. What we need is the general expression to calculate VIF for the kth predictor. In other words, the general expressions for inflated variance of k and minimum variance of k. As part of the lectures on simple linear regression model, we learned how to derive the minimum variance k of the estimated slope coefficient of the kth predictor. Denoted by where bk min is given by minimum variance of k equals where bk min equals sigma square divided by sigma 1 to n xik minus mean of xk the whole square, where sigma square is the variance of the standard error about the population regression line, which actually is unknown, and xik is the ith observation of the kth predictor from the sample, and xk bar is the mean value of the kth predictor from the sample. Inflated variance of the estimated slope coefficient of the kth predictor, denoted by where bk, when more predictors are included and some among them are correlated with this predictor, is given by where bk equals sigma square divided by sigma 1 to n xik minus xk bar the whole square multiplied by 1 divided by 1 minus rk square, where rk square is the r square value obtained by regressing the kth predictor xk on the rest of the p minus 1 predictors included in the model. Therefore, the general expression to calculate VIF k for the kth predictor is derived as follows. VIF k equals sigma square divided by sigma 1 to n xik minus xk bar the whole square multiplied by 1 divided by 1 minus rk square divided by sigma square divided by sigma 1 to n xik minus xk bar the whole square, which equals 1 divided by 1 minus rk square. When the correlation between the kth predictor xk and some of the other predictors included in the model is strong, then rk square increases, which in turn inflates the where bk to larger values. When the correlation between the kth predictor xk and other predictors included in the model is weak, then rk square reduces, which in turn results in where bk converging down towards where bk min. Therefore, higher the correlation, higher is VIFK, and lower the correlation, lower is VIFK. VIF quantifies the inflation. How to make the decision regarding multicollinearity using VIF? As a thumb rule, value of VIF greater than 4 but less than 10 warrants some investigation. That is, care is required in interpreting the results. VIF value greater than 10 implies action is required. That is, to identify the predictors that probably requires elimination. Further model building should proceed with the remaining set of predictors. Let's revisit the blood pressure data that we used in the previous lecture, and this time build the model with focus on how to detect multicollinearity using VIF and eliminate the problematic predictors. To begin with, let's build the model including all the 6 predictors and take a look at the Minitab outputs. Let's take a look at the VIF column in the coefficients table output. We find 3 VIF values that are greater than 4. These values of VIF indicate that each of these predictors is correlated with some of the other predictors included in the model. We need to understand which are the predictors that are correlated with each of these 3 predictors so that further action can be taken to minimize the VIF values in the model. The correlation table provides the means to identify the same. We observe weight versus BSA is the highest at 0.875305 and pulse exhibits a fairly strong correlation that is greater than 0.5 with age and weight and stress. Between weight and BSA, Since BSA measurement is not straightforward like weight, we choose to retain weight and drop BSA from the model. And since pulse is correlated with more than one predictor, we choose to drop pulse as well from the model. Dropping BSA and pulse from the model also simplifies the model, which is meaning simplifying the model is always part of the model building strategy anyways. We now rebuild the model including 4 out of the 6 predictors, dropping BSA and pulse. Let's take a look at the Minitab outputs and in particular the VIF column in the coefficients table output. We find all the 4 VIF values are less than 4, little over 1, which means there is hardly any significant inflation in the variances of any of the predictors included in the model. Monitoring VIF and taking necessary actions based on VIF values is an essential part of the model building. And we just saw with an example how we carry out those actions. Note that the model that we arrived at this stage is not the final one, as we see p-values of duration and stress are quite high. We already discussed the steps to handle these situations in our past lectures, especially the model building lectures. Hence, we do not go into those details again now. VIF is the means to detect multicollinearity. However, it is not necessary that eliminating the problematic predictors is always the solution. There are other ways to handle multicollinearity without removing the predictors. Finding the alternative ways to handle multicollinearity requires that one understands the reason behind the presence of multicollinearity. There are 2 possible scenarios. Multicollinearity is observed either because it is data-based or it is structural. Data-based multicollinearity. Multicollinearity in this case happens because of the way the data is collected. Often occurs in observational studies, though not limited. Can happen in experimental studies as well. Structural multicollinearity. This type of multicollinearity happens when new predictors included in the model that are derived from the existing predictors. Example, model that implements a polynomial expression in the regression function. Say quadratic regression function as in yi hat equals b0 plus b1 multiplied by xi plus b2 multiplied by xi square. In such a model, the predictor xi and the derived predictor xi square introduce high levels of multicollinearity that cannot be avoided. Let's understand each of these 2 multicollinearity in detail and the means to handle them without deleting the predictors. Let's start with data-based multicollinearity. Often happens because of poorly designed experiments in case of experimental studies, excessive reliance of available observational data, which happens in the case of observational studies. Very often, the possible way to correct the multicollinearity is to collect additional data. Let's illustrate that with an example. Here is the data used for Allen Cognitive Level, in short ACL study, that aims to test the relationship between ACL test score and the following 3 measurements for 69 patients. 1 vocabulary score and 2 abstract thinking score, both measured using Shipley Institute of Living scale, and 3 symbol digit modalities test score. Let's not break our heads on the conceptual details of these tests and just pay attention to the data relationship between the response variable ACL test score and the rest, which are the predictors. Let's first take a look at the scatter plots between the response and the predictor variables before looking at the regression outputs. The scatter plots do not show strong correlation anywhere amongst the 3 predictor variables. Regressing ACL score on vocab, abstract and SDMT yields the following VIF values. Note all the 3 values are well below 4. The rest of the outputs are not of interest for the current discussion. Let's treat this as scenario 1. For the sake of illustrating the data-based multicollinearity, let's derive scenario 2 from scenario 1 by degrading the sample data set. We derive a sample consisting only 23 data points from the scenario 1 sample that consists of 69 data points. As we said, we call this as scenario 2 data set. Watch the record numbers that we have selectively picked up from the original scenario 1 sample. They are not continuous. How did we choose the scenario 2 data set? Take a look back at the scatter plots and with the focus on the scatter plot between vocab and abstract. Let's zoom into this scatter plot. We see the data points represented in blue circles for 23 data points and red rectangles for the remaining 46 data points. A close look at the data points in blue circles reveal that they exhibit a strong correlation between vocab and abstract. This subset of 23 data points from the overall 69 data points form the data set for scenario 2. This is how we arrive at scenario 2 data set. We take a look at the scatter plots between the response and the predictor variables for scenario 2. As discussed, the scatter plot between vocab and abstract show strong correlation, while the rest two show lower levels of correlation. Let's take a look at the Minitab outputs for scenario 2 by regressing ACL score on vocab, abstract and SDMT. As expected, we see very large VIF values. Scenario 2 has resulted in multicollinearity. This multicollinearity is manually created one, created for the sake of illustration by carefully picking up a subset of the original sample data set that exhibit a strong correlation between two predictors. By this illustration, we try to communicate the message that at times multicollinearity could be observed purely because of the reasons related to inadequately or incorrectly collected data. Scenario 2 is the case where the data collected is inadequate. This kind of multicollinearity is called as data-based multicollinearity. The solution to address or correct this multicollinearity is to collect more data or collect data under correct circumstances. Collect more data as illustrated as part of scenario 1, which means increase the sample size from 23 data points to 69 data points. By doing so, we eliminated the data-based multicollinearity, which can be seen from the values of VIF, which existed because of insufficient data collection as illustrated using scenario 2, or in cases where data is collected incorrectly. Therefore, when we stumble upon multicollinearity in the model, one thing that we should examine is whether the data is adequate or collected without errors during the process. And if we detect any of the above discrepancies, collect more data and correct data and check if the multicollinearity is eliminated or reduced. Let's now turn our focus towards structural multicollinearity. Structural multicollinearity, as against the data-based multicollinearity, is an induced one. It is a mathematical artifact induced by introducing new predictors in the model which are derived from the existing predictors. As in the case of a polynomial regression model, y hat equals b0 plus b1 multiplied by x1 plus b11 multiplied by x1 square. x1 square is a new predictor derived out of the existing predictor x1, thereby introducing a strong correlation in the model between the existing predictor x1 and the newly introduced predictor x1 square. Let's understand the structural multicollinearity with an example. The problem at hand is to study if there is a relationship between exercises and human immune system. How to measure or quantify the exercise that an individual carries out and the immune levels. One way to quantify the exercise levels is to measure the oxygen intake, to be precise oxygen levels in the blood, and to quantify the level of immune system is to measure the immunoglobulin levels in the blood. Here is the sample consisting of data collected from 30 random individuals. Scatter plot between the response immunoglobulin level and the predictor blood oxygen level is presented below. The scatter plot shows a certain amount of nonlinearity. That motivates us to go for a polynomial regression fit. Regressing immunoglobulin levels using a polynomial regression function of second order onto the predictors that include blood oxygen level square in addition to blood oxygen level, we have the following output tables from Minitab. Oxygen in the tables above denote blood oxygen level and oxygen XQ denote blood oxygen level square. Oops, take a look at the VIF levels. Huge, 99.94. Rest of the outcomes look pretty okay, R square and its variance and p-values, etc. These very high VIF values are not unexpected. Scatter plot between oxygen and oxygen SQ display a strong correlation. Pearson's correlation coefficient equals 0.995, so high is the correlation. Therefore, by resorting to polynomial regression, we have introduced structural multicollinearity. As discussed earlier, the regression plane rests on a narrow band where data points are concentrated along a straight line in the oxygen and oxygen SQ plane. We know such a regression plane is subjected to large swings resulting in large variance in the estimated slope coefficients across samples due to sampling variations. How to handle this structural multicollinearity? One known common technique is centering of predictors. Subtract the mean of the predictor values x bar calculated from the sample from each of the predictor values xi, such that we derive a new predictor x star where x star equals xi minus x bar. The mean value of oxygen x bar, that is oxygen bar from the current data set, is 50.64. Subtract oxygen bar from each of the predictor values oxygen I to get x star, that is oxygen star, where oxygen star equals oxygen I minus oxygen bar. Now we go ahead and compute oxygen SQ star from oxygen star in order to arrive a second order polynomial regression fit between oxygen star and immunoglobulin levels. Before arriving at the polynomial regression fit between oxygen star and the immunoglobulin levels, let's take a look at the scatter plot between oxygen star and oxygen SQ star as against oxygen and oxygen SQ. The data points in the scatter plot between oxygen star and oxygen SQ star are well spread out, suggesting a more stable regression plane across samples with minimal swings. While data points in the scatter plot between oxygen and oxygen SQ, as already discussed, are concentrated along a straight line. Pearson correlation coefficient between oxygen star and oxygen SQ star drops down to 0.219 as against the one between oxygen and oxygen SQ, which was at 0.995. Let's now take a look at the Minitab outputs by regressing immunoglobulin levels using a polynomial regression function of second order onto oxygen star and oxygen SQ star. Take a look at the VIF values. VIF equals 1.05, huge drop in the VIF values, signifying no multicollinearity whatsoever. Rest of the outcomes look pretty okay, R square, its variance, p-values, etc. As the R square and its variance suggest around 93%, the estimated polynomial regression function also seem to offer a more than acceptable fit. Centering predictors is therefore a useful technique in circumventing the structural multicollinearity. Let's take a look at the estimated regression function IgGi hat equals 1632.3 plus 34.0 multiplied by oxygen I star plus 0.536 multiplied by oxygen SQ I star, where IgGI hat is the predicted value of the immunoglobulin level at the given value of oxygen I star. Since oxygen I star equals oxygen I minus the mean value oxygen bar and oxygen bar equals 50.64, the estimated regression function in terms of the oxygen level in blood, that is oxygen I, the original predictor, is given by IgGI hat equals 1632.3 plus 34.0 multiplied by oxygen I minus oxygen bar plus 0.536 multiplied by oxygen I minus oxygen bar the whole square. We used this regression function that we arrived as a result of centering the predictors to predict the immunoglobulin level of a person whose oxygen level in the blood is at a certain value. That completes our understanding on structural multicollinearity and the techniques to circumvent the same. That concludes our understanding on the concepts behind multicollinearity, its impacts and consequences, the statistic namely VIF, and the ways to handle multicollinearity in model building. See you back soon with the next lecture on this playlist of videos. Bye for now.